Hey everyone, and welcome to the Calculus 1 Exam 3 review. I am your lovely host, Professor Armstrong. So Exam 3, Calc 1, has about 18 questions. Depending on your professor, you might turn some in, you might not. For my class, I have 8 problems that I have my students turn in. So if you're watching this, then obviously I like to always remind you that there's some good stuff for you. So let me go ahead and screen share so we can get this review started. So if you come in to our course, because that's where you found this video, our online math resources, and you scroll down to calculus, you go into test review materials. Hey, there's the instructional videos that we have. Some great things in there, a mixture of my notes. Also, Dr. Macon videos are in there, which his videos are amazing. But here are the test reviews. Here are the previous reviews that you see. We have a version A for exam 1, a version B, or sorry, a version A for exam 2. We are currently working on exam 3. And there will be an exam 4 that I have out here, as well as the final exam, just so you know. But here is the document that I'm going to be working off of. We are currently working on the solution guide for it, and the video will be posted once we are finished with this and Zoom gets back with us with the link to share the video. So here's all of our good stuff: past, present, and future. With that being said, I'm going to go ahead and close this up. I've got my Decimos calculator ready. You can also have your TI-84 calculator ready. I don't recall using it very much for this, if at all, when I was actually going through and working up an answer key for everything. And so let's get started. So here is our review. So question number 1 is all about finding when the particle, because we have a position graph here. So this is like your f of x position of a function of 2 particles are shown, where t is measured in seconds. And down here, we're going to have intervals. And we want to know, when is the particle positive? When is the particle negative? When is the particle speeding up? When is that particle speeding down? And there are 2 parts to this. So we have a total of basically about 4 answers to give. Now, I think when it comes to the exam, we're going to narrow this down where maybe you just talk to us about the positive and negative part, or maybe you talk to us about the speeding up or speeding down. You're not going to have both, but it's good practice to review both of these. So I'm going to do a quick redraw of this graph on my piece of paper. So just bear with me a moment. And there's nothing on the y-axis. And that's a-okay. And there. And we're going up there. Whee! I love sound effects. Okay. So actually, and I'm gonna, no, I'll just wait, because again, I don't know how much room I'm gonna take up. So first thing is, we want to know when the particle or particles is positive. So what that means for us is we want to look at the first derivative of this function. Well, in our case, I shouldn't say f, it's s, our position function, which will tell us about the velocity. And so that's really velocity. And we want to know when this thing is greater than 0. Because if you are greater than 0, that means we're talking about a positive derivative. And that means that f, or our s function, is increasing. Okay. So this means that it's positive. If we want to know about when a particle is negative, we want to know when S prime, or in other words, the velocity, is less than 0. Because that means you're negative for the derivative, which means that S is decreasing. Okay. Now we could easily see this on our graph, but I want to always review things that we know. Remember, when you're looking at the position function to help us create intervals, remember we look for critical numbers. And when we have critical numbers, you look at two things. You look at the zeros, and we look at when F prime does not exist. Okay. So in other words, when you look at zeros, you're looking at when F prime is equal to 0 and when it does not exist. Okay. So in other words, when you're looking for those critical values, these numbers here, the real big thing is you're trying to find max and mins. That's what this all boils down to. So that's what's going to help create our intervals, because this is all about, does it have max and mins? And by it, I'm talking about the function, our position function. Okay. So granted, we don't have a function to set equal to 0. The cool thing is this function is continuous, so there are no bad values. So that means our derivative is going to be continuous. So we're not going to run into a does not exist piece here for us on this, because we're going to be a-okay. All right. So if we look up here, this guy is a max. This guy is a min. Our graph is going to be contained from 0 to 4. I'll put that in. 1, 2, 3, 4. So we know our critical values. Okay. We know that they are 1 and 3. We already know that they're a max and a min. Okay. Because this is our position function. So that's guaranteed. So what we want to do now is we want to find those intervals. So I always set up like a little number line. And then I've got my 1 value and I've got my 3 value. And we want to talk about, well, what is F prime doing? And then that lets us know what F is doing. So if you're looking at this, well, what's going on from 0 to 1? Well, if we think about our derivatives, these are all positive derivatives. So if I draw in a tangent line as best as possible, that's a positive slope. So we're positive here, which means F is increasing. Oh, that makes sense. Okay. Well, what's happening between 1 and 3? Because that's my next interval. Well, if I draw on a tangent line as best as possible, oh, look, that's a negative slope, which verifies that, yes, this guy is decreasing. There's always a method to my madness here, just so you know. And then, well, what's going on from 3 on to 4? I should put zeros down here because that's the end of our line. We're not going to go past that. Put a 4 up here. That's the end of a line. We're not going to go past that. So what's happening from 3 to 4? Well, if I draw in a tangent line, it looks somewhat like this. There's my tangent line. So that's a positive slope. So we're increasing. So now we know when the particle is positive and when the particle is negative. So we can answer I real quick. So my particle is positive from 0 to 1. And my particle is positive from 3 to 4. Part 2, so there's our I or 1, part 1 question. Part 2, when are we negative? Well, we're negative from 0 to 1, or sorry, 1 to 3. There's our negative, and that is interval notation. Okay. So now for part 3 and 4, we want to know, when is the particle speeding up? When is the particle slowing down? And this is why I wrote out this information that I have right here, because this is going to help us in the next piece in 3 and 4. Okay. So in 3 and 4, this is all about speeding up and slowing down. Well, a particle is speeding up, and this happens when the first derivative, or in other words, velocity for us, is, the first derivative, which is velocity, and the second derivative, which is acceleration, are the same sign. So velocity is positive and acceleration is positive. We're speeding up. Velocity is negative and acceleration is negative. We're speeding up. Where on the other side, the particle is slowing down when the first derivative, which is velocity, and the second derivative, which is acceleration, are different signs. So velocity is positive, acceleration is negative, or velocity is negative and acceleration is positive. So again, we're going to think about, well, okay, so we need to know about the second derivative. All right, so the second derivative, okay, it's all about the inflection point. And remember that the inflection point is where it changes from concave up to concave down. So you can see in our picture, we've got a concave down here. We've got a concave up. With this picture, they're trying to make the inflection point very easy for you. So hopefully you see that the inflection point really is here at the 2 value. This guy is the inflection point. So I'm going to again draw my little line, and I've got a 2. Okay. And we'll talk about what F double prime is and how that is affecting F, because I think that's important. And again, this number 2 is just like finding a critical value that told us about max and mins. So if you were doing critical numbers here and we actually had an equation, you would have to do the same thing. You would need to look at the zeros. But this time we're talking about when F double prime is equal to 0. Or look at when F double prime does not exist. And again, we're not going to have to worry about that, because when you find these critical values, that tells you all about inflection points. Okay. So again, we didn't have the equation. We had to look at our picture, and this is our inflection point for sure, because they want to keep things easy for you since you don't have a lot of information about the equation. All right. So, well, what is F double prime before that? Okay. Well, if you look at that, it is concave down, which means that F double prime is negative there. Because it is concave down. If we look at the second piece, this is concave up after 2. And again, this is from 0 to 2, we're concave down. And then 2 to 4, we are concave up, which means that F double prime is positive. Now that we know the signs based off of our information, we can answer the speeding up and the slowing down. See, this is why I didn't. Because my part A is continuing on to the next page now. Okay, so I'm going to need some information here. So we're on part 3. And we're on part 4. Talking about speeding up, slowing down. So our first interval where F prime is positive, okay, is from 0 to 1. So if I come down here, I only have 2 intervals here. We have 0 to 2 and 2 to 4. So where does 0, 1 fall in? It falls in down here in this interval. So we know that 0 to 1 is positive. We know that down here in this interval, the 0 to 1 would be a negative. So those are opposite signs. Positive, it's negative. So that means 0 to 1 falls in the slowing down category. Because F prime was positive and F double prime was negative in this interval. So now we jump back up. Okay. I like to go in order, so I'm going to jump over here to the 1 to the 3. So the 1 to 3, when I come down here, oh my gosh, it falls into both of these intervals. So that means we're going to have to break it up because the 1 to 3 interval falls in both of these. So we're going to look at this as 2 intervals. We're going to look at it as from 1 to 2. And then we'll do the 2 to 3, which will complete the rest of that interval. Okay. So let's do 1 to 2. Okay. So we know that 1 to 3 is all negative. We know that 1 to 2 to complete the rest of this interval is negative. Oh, they're both the same sign. So we're going to go over here and the interval 1 to 2 is going to be speeding up because F prime is negative and F double prime is positive. All right, now let's look at the rest of that 1 to 3 interval. So now we're going to look at 2 to 3. Well, again, because 2 to 3 falls in here, we know that it's negative. So F prime is negative. Now 2 to 3 follows in this interval down here. So F double prime is positive. So F prime is negative, F double prime positive. Oh, that's a conflict. They're different. So 2 to 3 is going to be slowing down because as we just said, F prime is negative, F double prime is positive. And last but not least, we have one more interval from 3 to 4, and that is a positive interval. So F prime is positive. And 3 to 4 follows in this interval, which is also positive. So positive and positive, that means we're going to speed up. So 3 to 4 follows in the speeding up category because F prime is positive and F double prime is positive. And there's our answers. We are speeding up on the interval 1 to 2 and 3 to 4. We are slowing down on the interval 0 to 1 and 2 to 3. Part B is just like this. Okay. So let's do part B. Let me go ahead and get my graph for this. I won't have to do as much writing because we're going to be doing the same thing again. So we're working from 1 to 4. Okay. Thank you for bearing with me as I draw my graph as best as possible. All right, answering the same questions. Okay. So we want, I'll just put my little line out here of F prime. Almost forgot what I was doing. So what are the critical values right now? What are the critical numbers? Or in other words, where do we have a max and a min for F prime? So F prime critical numbers, they are going to be 3. That's it, because that is a minimum. So I'm just going to put a 3. And let's talk about what's going on. So as I draw in my tangents from 0 to 3, we get, if I draw on a tangent, that's what it looks like roughly. That's a negative number. It's a negative slope. So that means F is decreasing. Okay, because again, over here, I think my voice just cracked. My slope is negative, and my slopes down here are still negative. Now, as I get on the other side from 3 to 4, my slopes, if I draw on a slope, oh, look at that. That's a positive. So we are increasing. Okay. So we now know for part I that the particle is positive on 3 to 4. Okay. We also know double I, or part 2, that we are decreasing from 0 to 3. Okay. Now jumping into the double prime to help us answer part 4. So there is one inflection. Well, actually, there are 2 inflection points. Okay. One of your inflection points happens here at 1. And another inflection point happens here at 2. Because this is concave up here. This is concave down. This is concave up. So again, thinking about those, our F double prime critical numbers are 1 and 2. Okay. So F double prime, 1 and 2. Oh, again, I should probably mark that we're only going from 0 to 4. 0 to 4. Okay. So from our graph, we can see that this is concave up here, which means that F double prime will be positive on this interval from 0 to 1. we see that we are concave down here, which means that we will be negative on 1 to 2. And we can see that from 2 to 4, we are concave up here, which means that F double prime is positive. So now, with our information, knowing about positives and negatives, we can talk about speeding up and slowing down. So part 3, we are ready to answer now. So I'll always start up here. This is positive from, well, actually, let's go with the negative. Let's start from left, working our way right. So this is 0 to 3. So where does 0 to 3 fall? Oh my gosh, 0 to 3 falls in all 3 of these. So again, we're going to break it down, and the double prime helps us break it down. So we need to look at 0 to 1. So 0 to 1, well, that falls in here, so that's negative. And 0 to 1 is positive, so that means we're slowing down. 0 to 1, we're slowing down because F prime is negative. F double prime is positive. Okay. Then we got another interval from 1 to 2. So 1 to 2 is still negative. Okay. It's negative. And 1 to 2 is negative for double prime. So a negative F prime, a negative F double prime, that means we're speeding up. From 1 to 2, we are speeding up. So F prime is negative. F double prime is negative. Okay. And then from 2 to 3, well, 2 to 3 is in here, so it's negative. 2 to 3 is in here, so it's positive. So again, we're slowing down because F prime is negative, but F double prime is positive. And that's going to end that answer, I know for sure, because our last interval is from 3 to 4. 3 to 4 is positive. 3 to 4 happens in here, which is positive. Hey, positive and positive means that we are increasing our speed. We're speeding up. And there we go. That's what they are after on number 1. Okay. All right. Let's jump over to number 2. So if you are in my class, number 2 here is one that I would have turned into me. So just know your professor. So here, let's take some things. It says the radius of a spherical ball is increasing at a rate of 2 centimeters per minute. Oh, so right there, we know R prime is equal to 2 centimeters per minute. I called that R prime, but you can also call it dr dt because this is all about with respect to time. Okay. So it says at exactly what rate in centimeters squared per minute is the surface area of a ball increasing when the radius is 7. All right, so we now know the radius is 7 centimeters in the end, and we want to know surface area prime of our sphere. So this is what we know. This is what we're after. The rate of change for surface area when R is 7. Okay, and again, that would be d surface area over dt. All this is with respect to time. So again, kind of just showing you a picture because I like pictures. So here's my sphere. Oh, that should be dotted. because it's behind my figure, Mr. Armstrong. There we go. 7 centimeters. That's what we know. Okay. So the first thing is there's got to be some formula we know. And surface area of a sphere, absolutely. The surface area of a sphere is equal to 4 pi r squared? No, cube. No, squared. Because it takes 4 circles to cover a sphere. Kind of interesting. If you take apart a baseball, you can kind of see those 4 circles. All right. So what we need to do now is take the derivative of this with respect to time. So in other words, that means we're going to do an implicit derivative. Because this is surface area, this is r, none of these are the time variable. So derivative of surface area prime, equal to, this is a constant, so we don't worry about that. We just got to take the derivative of the r squared. So the 4 pi is still there, it's constant. Derivative of r squared is 2r r prime. Because again, we're not taking the derivative with respect to r, we're taking the derivative with respect to t. So you basically take the derivative of the r, which is 2r, and then you slap an r prime after it. Okay, it's kind of a Mr. Armstrong shortcut. There's a little, you should remember the mathematics that's really going on behind this. Okay, so here's what we got, just a little bit of cleanup. So surface area prime is equal to 8 pi r prime. And so now we just take the information we knew up here and we plug in, because we know the r, it's 7. We know the r prime, it's 2. We're looking for that answer. All right, easy peasy. So that will be 8 pi times 7 times 2. So just go to our handy dandy calculator. Surface area prime. All we really got to do is take 14 times 8, and we get 112 pi. This will be centimeters squared per minute. So there's an exact answer, but you should always make sure that you read the directions. And if the directions say round, I think I've seen this one, and it might have you round to 2 decimal places. So you take 112 times pi, and to 2 decimal places, you got 351.86 centimeters squared per minute. So depending on what they ask for, there's the exact, and there's the rounded to 2 decimal places, to the nearest hundredth. Okay. So there's question 2. Jumping over to question 3. Again, if you are taking my course, this would be a question you would turn into me. But if not, do as your professor says. So we got this 4x squared plus 16y squared equal to 100. They also tell us down below that dy dt, oh, interesting. So we're taking this with respect, the derivative with respect to t. So that means we're going to be doing another implicit derivative, because our variable that we're concerned with is the t. So dy dt is 1/4. Oh, right there, it's telling us what they want us to find. So we want to know what is dx dt. And they also tell us that x is equal to 3 and y is equal to 2. Okay, cool beans. Let's take our derivative, and then all you're going to do, just like what we did on number 2, is plug in, kick me out an answer. All right, so again, it's an implicit derivative. Our derivative is t. So if I take the derivative of this, I'm going to get 8x x prime, because x is not the derivative I'm differentiating. It's t. Plus, if I take the derivative of 16y squared, I will get 32y y prime, equal to the derivative of a constant is 0. Okay. So now all we got to do is plug in. So 8 times our x value is 3. We're actually looking for this guy. We're looking for dx dt. That's what this is. So I'll just leave it as x prime. Plus 32 times our y value is 2. Our y prime is 1/4. Equal to 0. So doing some quick cleanup, 8 times 3 is 24x prime, plus 32 times 2 times 1/4 is 16, equal to 0. Okay. So if we bring the 16 over to the other side, 24x prime equal to negative 16. Divide by the 24. X prime is negative 16 over 24. But as math students, we always reduce. And negative 16 over 24 is equal to a negative 2/3. There's our x prime. Our dx dt. All righty. Question 4. And that was question 3. So question 4, again, I believe I would have this turned in to me if you were in my class. And we want to find critical values of hyperbolic tangent, or sorry, the inverse of hyperbolic tangent x to the 9th. Okay. So this right here, in order to find, well, let me start again. Again, critical numbers, we talked about this earlier. In order to find critical values, okay, we need to do 1, zeros, which is f prime equal to 0. And we need to figure out when f prime does not exist. Okay. And usually this happens when you have a rational and you take the denominator and set it equal to 0. Usually, but there are other cases. So let's get g prime of x. So this is a chain rule. Inverse hyperbolic tangent is the outside, and x to the 9th is the inside. Okay. So we need to take the derivative of inverse hyperbolic tangent on the outside. And I'm going to be honest, I don't have that answer. So let's just look it up. Inverse hyperbolic function. Hopefully they'll throw derivatives at me on this. And it looks like they do. Let's go to images. Maybe I'm gonna have, oh, no. Here we go. So the derivative of hyperbolic tangent is 1 all over 1 minus x squared. Okay. So, but that x squared for us is really an x to the 9th. So 1 over 1 minus our x squared. I'm on the wrong page. Our x squared is really x to the 9th, and that is squared. And then we're going to multiply this by our derivative of the inside. So that is 9x to the 8th. So again, some cleanup before we find those critical values. It's really just moving this into the numerator and then multiplying that piece out. So we get 9x to the 8th all over 1 minus x to the 18th. Okay. All right. So what we got to do now, we're going to take, and let's make sure on that derivative real quick. Yep. 1 minus x squared. Okay. Just wanted to double check. So in order to find our critical values, we want to find the zeros. So in order to find the zeros of a rational, you just take the numerator and set it equal to 0. So 9x to the 8th equal to 0. Okay. So if we divide by 9, we'll find out we get x to the 8th equal to 0. And if I take the 8th root of both sides, we'll find out that x is equal to 0. There's one critical value. For the does not exist, because this is rational, this will only not exist when the denominator is equal to 0. Okay. So we subtract 1 over, divide by -1. And then we got to take the 18th root of both sides. Well, if you take the 18th root of both sides, you're really taking the 18th root of 1, which is 1, but because it's even, it's really a plus or minus 1. So we have 3 critical values where this does not exist. Or sorry, 3 critical numbers at 1, -1, and 0. We got 2 values where the function does not exist as the derivative. Okay, so there we go. There's our critical values. We don't want anything else. All right. So just kind of, again, a rule of thumb, a couple things that kind of come up in here. Even roots of a number always have a plus or minus in front of the answer. Odd roots of a number, well, we don't worry about that. There's no plus or minus in front of that answer. It's either positive or negative. Another piece to be careful of, because I have seen this happen, is that sometimes they will throw negatives at you when you do your roots. Remember, an even negative number root, we're going to say does not exist because it creates really complex values. An odd number of a negative, an odd root of a negative, remember the negative pops out front, and then you deal with the odd root of the number. So keep those in mind. I have seen those cases kind of pop up in this problem. Okay. Number 5. And for my class, that would be something that you would turn into me. All right, number 5, we got a picture here. And we want to know what are the absolute maxes, absolute mins, local max, local mins, and neither. Okay. Just writing down. So remember that an absolute max means the highest of the high. Okay. So if we look across here, where is the highest y value? Well, that happens here. And is that an absolute max? Absolutely. You can have they don't have to be curved. They can happen at corners. Okay. They can happen at disjunctions. Okay. Absolute max means it is the highest Y value and there's no one else higher than that. So if you look at this, that absolute max happens at R. Okay. Also remember that absolutes can happen at endpoints, but locals cannot. So A and B, or sorry, A and S cannot be locals. Okay. Because those are the endpoints of my graph. All right. So where's the absolute minimum? Where is the lowest of the low? So I want some point up here that has the lowest Y value. And that's going to happen at A. And that is A-OK for absolutes because absolutes can be endpoints. So again, R is our absolute max. A is our absolute minimum. Now for locals, remember locals are all about an area, okay? A neighborhood. You're not looking across all of this. You're looking at a neighborhood around a point, okay? So when we talk about a local max, think about it like the top of a hill and the bottom of a valley, okay? So obviously this cannot be a local max. It's too low, okay? Plus locals cannot happen at endpoints. So we come over here. So both of these dots right there represent B, okay? So if we look at this guy, because we're looking for maxes, is that a max? So if I create an area around this, kind of like what I'm circling, is this the highest Y value within that area? And the answer is yes, because this is pretend like, let's say this is 4, the Y value is 4. If I move to the left of 4, I have values that are lower than it. If I move to the right of 4, I jump down here and obviously these values are lower than that 4. Okay, again, I was hypothetically saying this was 4. So this meets the requirement of a local max because a neighborhood around it, this is the highest of a high. Well, no, sorry, not the highest of a high, but the highest within that neighborhood. So B has a local maximum. If we come over here, I can't look at this the same way. This was a closed dot. This is an open dot, which means that if let's say this was 4, this was 4.5, that means I'm going to get really close to 4.5 up here, but never touch it. So I cannot say this is a local maximum because we don't include this because it's an open circle. So we got to throw out C. This is really low. So obviously we can't do D. What about R? It's an absolute maximum. Can absolutes be locals? Absolutely. Again, as long as the absolute is not an endpoint. So R is also a local maximum because it is the highest point in a neighborhood around it. Okay, it's actually the highest of the high. No one beats this Y value, whatever it might be. And then obviously we don't worry about this because it's an endpoint. Locals can't happen at endpoints. So let's do the same logic with D. Okay, do I have any local minimums? So I can't use A because it's an endpoint. So I come over here. Well, we already said this was a local maximum. Local maximums can't be local minimums, okay? So we come here to C. So here's where my point is at, that's good. But if I create a neighborhood around it, yes, all these values are bigger than it, but if I create a neighborhood over here, if I go after C, my Y values are still shrinking, getting smaller. So C cannot be a local minimum. It's impossible because there are Y values that are lower than it right in the neighborhood of it. So we go to D. Now this one is the bottom of a valley. That is definitely a local minimum because there are Y values around this that are always going to be higher than it than what happens at D. R is a maximum, so we don't worry about that. This is an endpoint, so we can't worry about that. So we only have one local minimum, it's at D. We have two local maximums, one at B here and one at R. Now, part E is, well, is there anybody we didn't talk about? And yes, there was. We didn't talk about C and we didn't talk about S. So this is what falls into E, because C and S are none of those answers. They're not local maxes, they're not local mins, they're not absolute maxes, they're not absolute mins. They're just points on my graph. And there you go, there's number 5. All right, number 6, we're gonna sketch a graph. Cool thing is on this one, this is all going to be on your exam, like a multiple choice. But I wanna go ahead and sketch this by hand, so that way we understand what's going on. So we've got a graph here, F prime, that is continuous, okay? So we know F is continuous, and it's on an interval of 1 to 7.5. So this function is not going to continue on and on and on. It's stuck between 1 and 7.5. We also know that it has an absolute max at 6, and we have an absolute minimum at 7.5. It also tells us we have a local max at 2 and a local min at 4. Okay. Now their graph has y values. Granted, with this information, we know without the actual function, we don't really know what those y values are, which is why I want to sketch it. The only thing that we do know is that we got an x-axis that goes from 1 to 7.5 at least. Okay. So I'm gonna go 1, 2, 3, 4, 5, 6, 7. And I'm gonna go actually out to 8. 2, 4, 6, 8. Okay. So let's take this. We know that our graph starts here at a 1 somewhere and ends here at a 7.5 somewhere. Okay. So let's take a look at this information in here and see what we know. So it says we have an absolute max at 6. So absolute means highest of the high. So I need to put a dot at 6 that's up pretty high on the y-axis. See, it's up pretty high. So I can't have any other points be the same as this or above it. All right. So then I've got an absolute minimum at 7.5. Now that's cool because look, 7.5, 7.5. So that means this is an endpoint. So at 7.5, I need a lowest of the low. So I'm going to put that there. So there's my absolute. I don't want anybody higher than that. Here's my absolute minimum. I don't want anybody lower than that. Okay. So now we have a local max at 2, which means, again, let's make this look like a maximum, but it can't be higher than 6. Okay. So I need my dot. I'm going to put it high like that. There we go. That's a good place for that dot. And we'll make sure that this comes up into a maximum. Okay. We also have a local minimum at 4. So again, can't be lower than this dot. So I'm just going to place it up a little bit higher. So we'll want to make sure that our graph swoops up into this and then swoops down into a minimum for that. And then it will swoop back up to this guy and come back down. Now, the only point that we don't have is the first dot. Well, now you got to think about this. Okay. My first dot needs to be higher than this point on the y, but lower than that point. Okay. Because my first endpoint is not an absolute. So it's got to be between my two highest and lowest points. So I'm just going to put it right in the middle. Why not? Okay. So as we said, all we got to do now is like connect the dots. So I'm going to curve up into this guy. I'm going to curve down into that one, curve up, and then curve back down. So it'll look something like this, my graph. There we go. There's our graph. And we can double check this. Yep, definitely a local max, definitely a local min. There's my absolute. There's my absolute. And we are from 1 to 7.5. Perfect. So let's go back, and we want a graph that looks like this. Cool thing is, I drew this by hand, but you can, because it's multiple choice, you can just come down here and take a look. So this looks like our graph, but the problem is this 7.5 here is a little higher than that 4 Y value there. So that's unacceptable. That would make the 4 the absolute min. So that's why we throw this out. This graph is not even doing what we did. We started going up from 1, increasing. It's decreasing. So it's not B, it's not A. Here we've got an absolute. This looks like my graph. So we know the answer is C. And again, in part D, this thing messed up because it's decreasing. It should have been increasing from the very beginning. C is our answer. Number 7 is just like this. Again, we got a function f is continuous from 1 to 5. We have an absolute max at 2. We have an absolute min at 5. And we know that we have a critical number 4. And we also know that that 4 is not a local max or min. Okay. So that 4 is not a local max or min. Okay. All right. So let's draw this by hand and go from there. So again, just going to draw me a short little graph. 1, 2, 3, 4, 5. Okay. So we've got an absolute highest of the high at 2. So I put that pretty high. We got an absolute lowest of the low at 5. And cool, it's also an endpoint. I'm going to keep that pretty low. We've got a critical number at 4, but it's not a local max or min. So what that tells us is that it's probably an inflection point. Okay. It's probably an inflection point. So I'm going to put some sort of dot right here. And we're going to make that look like an inflection point, because inflection points aren't maxes or mins, but they do show up as critical numbers. Okay. Now, the only thing that we don't have is the 1. So we just can't make it lower than our endpoint here and higher than what happened at 2. So I'll just put it right there. Put it right in the middle. So if I draw my graph, I swoop up into that. And then I'm going to come down. And come down. So it's kind of like we made a concave up and a concave down there. Okay, so there's what the graph looks like. So let's check what they got out here. So actually, A looks like it. A looks like our graph. D is kind of close, but our 1 value is actually an absolute in this one, and it was supposed to be the 5. So A is our choice. And there you can see, hey, it is an inflection point. Concave up, concave down. Okay. All right. Number 8. Number 8. So we got a graph right here. And again, we want you to state for part A, the absolute maximum values. In part D, the absolute minimum values. Okay. We also want the local maximum values. And this one, I think it might have been a typo, but I don't know. We're going to answer it both ways. This one says local minimums. I think it was supposed to be local minimum values, but we'll just answer it both ways since everything else is all about the values. And it does say value up here. That's why I was thinking this might be a typo, but it's fine. It's an easy question to answer both ways. So again, these things are asking for values. So when it asks for values, that means it does not want to know where it's at. In other words, it doesn't want the X values. It wants the Y values. Okay. So if your question says, what's the absolute maximum? That's asking about the X value. If it says, what is the absolute maximum value? Then it's asking about the Y value. So A, B, and C are all about the Y value, which makes me think that D was supposed to be about the Y value as well. But D, because it does not say value, that means this one wants to know about the X. Okay, but we're going to answer this for the Y value as well. All right. So for part A, absolute maximum Y value. What is the highest of the high Y value? And that will be happening at 5. So the X value is 4, but its Y value is up here at 5. So our absolute maximum value is 5. Well, our absolute minimum value, where is the lowest of the low? And unfortunately for that one, it does not exist. Okay. So if you look at all of our lowest Y values, here's a low Y value, but it's not the lowest of the low because over here, these Y values are lower than it. This is like 1.5 right there. So that's lower than 2. And again, the same thing here. This is the bottom of the valley and it's at 2, but that's not my lowest Y value. Again, that's not a low Y value. That's 3. These guys were lower than that. And then over here, all right, here's the question. Because this is an open circle, is that an absolute minimum? Because this guy at 1 would be the absolute minimum. So the question is, does that open circle affect that or not? And it does. Because this is an open circle, it means that that Y value we're never going to get to. Okay, it's like your annoying brother or sister coming up to you, be like, I'm not touching you, I'm not touching you, I'm not touching you. We're going to get really, really close to that Y value of 1, but we're not going to touch it. So in here, do we have an absolute minimum? No. The answer is a D and E. It does not exist. Okay. If this was a closed dot, then we would have said 1 is the absolute minimum value. Okay. But because that's an open circle, we throw it out. All right. Local maximums. So again, they can't be at endpoints. So we got to look in here. So where are our local maximums? Well, that's the top of the valley, but unfortunately, or the top of the mountain, but unfortunately it's an open circle. So we can't talk about this Y value of 4. So here's the top of the mountain. We can talk about that. And it's also our absolute maximum. So we have a local maximum value of 5 happening at the X value of 4. So we've got a local maximum there. We can talk about that of 5. And right here, as we go back up into the top of this mountain, if I create a neighborhood around this dot, because it is closed, actually is a local maximum because all the Y values going over here to the left of it are going to be smaller than 4. And all the Y values over here to the right of it are definitely smaller than 4. So we also have a local maximum at 4. So our two y values with local maximums are 5 and the 4. And then now local minimums. Do we have any local minimums? And absolutely we have local minimums. Okay. So if we look at what's going on right here, that is definitely a local minimum. Okay, because it's the bottom of the valley. And what's the y value? 2. If we come along, oh, look right here. That's definitely a local minimum. Oh, and I said the y value was 2 over here because this says local minimums. I need the x value. So the x value is 2. So, well, the y value is 2, the x value is 2. Well, that's cool. And then over here, this is also a local minimum. And we don't worry about over here because this guy right here is not included. This guy right here is not included. So we do have a local minimum right here. And that x value is 5. The y value at 5 is 3. So I'm going to kind of put a little parenthesis, local min values for this question were 2 and 3. So just to show you what I did. So these are all y values, except for these guys. Here are the x values, but I put over here in parentheses their actual y values. Okay. And there we go for number 8. Moving on. Number 9, this would be one that I would have my students submit if you are in my class. So again, we're looking for critical numbers. We are on a solid, I shouldn't say solid. We are on an interval here, so that's good. So we're not going to go outside of 0 and 2 pi. So we don't necessarily need to worry about n denotes any arbitrary values because we are in a contained interval. We're not going to go outside of that. So we have our function f of theta equal to 10 cosine of theta plus 5 sine squared theta. Okay, again, we're looking for critical numbers. So we've already been talking about this a lot. The critical numbers, and I put that as f prime. That's just f, silly Mr. Armstrong. So critical numbers for us are going to happen when we look at the zeros. In our case, we want to know when f prime equals 0. And when we look at when this does not exist, f prime does not exist. We look at those. All right. So let's find our derivative. Well, actually, before that, I want to rewrite this so that way you understand what something looks like. This squared part right here, just so you know, really looks like this when you consider this. So 10 cosine theta plus 5, and it is parenthesis sine parenthesis theta parenthesis squared. You're going to figure out the sine and then squared. So this is really, excuse me, chain rule. The power represents the outside, the sign represents the inside when you deal with that one. Okay, so that's important. All right, let's do the derivative now. So constant, we're just going to write down what is the derivative of cosine, and I believe that's negative sine. I can't always remember these things. So this is why some of you might get a chance to have notes. I would write some of those things down. All right, trig. We'll just go trig function. Oh, nope. I don't want videos. I just want derivatives. Might have to actually put the word derivative in. Yeah, I do. Function derivatives. There we go. There we are. So just looking at this picture, cosine, yes, negative sign. I just wanted to double check that. I was pretty sure it was that, but you know, signs are important. So negative sine theta, and derivative of sine is cosine, and that's always positive. So in here, I'm gonna write down the 5. So we're gonna do the derivative of the outside. So the 2 is gonna shoot in front. And 2 minus 1 is 1, and we keep what's inside there. So sine theta. So there's the derivative of the outside, 2 sine theta. Derivative of the inside, well, what's the derivative of sine? And that's cosine, as we just talked about a moment ago. So there's the derivative of the last piece. So some quick cleanup. F prime of theta, I'm going to put negative 10 sine theta. 2 times 5 is 10. And we've got sine theta cosine theta. Okay. So now what we're going to be worried about is when this thing is equal to 0. But before that, to kind of help us along, because I see this real quick. Hey, look, both of these have 10s. Both of these have sines. Let's go ahead and pull that GCF out. And because this first guy is negative, I always like to pull out a negative with it. So I'm going to pull out a negative sine, or negative 10 sine theta. This is really going to help us when we're solving for zeros too. So that'll be a 1 because I took all that out. Plus, well, that'll just leave us with, sorry, that's not a plus anymore because I pulled out a negative. That will be minus cosine theta. So now let's take zeros, which will take the negative 10 sine theta times 1 minus cosine theta equal to 0. And then we also want to know when this does not exist. Well, the cool thing is that sine exists everywhere. Cosine exists everywhere. So there's not a place where these two do not exist. And if you wanted to double check that, go into Desmos, plug in your derivative or plug in this derivative. Doesn't matter which one you plug in. And you'll be able to see that, oh, this thing exists everywhere. So you're actually not going to worry about the does not exist case for this because these always exist. They're continuous. No problems. Okay. All right. So we don't worry about that. We just worry about this case. Well, there's a reason why I pulled out that GCF because these two are factors. And what do you do when you have two factors being multiplied and equal 0? You set them equal to 0. So what you're doing right now is you're going right back into what you did in trig class. And you're solving a trigonometric equation. About, again, just wrote a theta. This should just be 0. And then we're going to set 1 minus cosine theta equal to 0. So if we divide by 10, we find out that sine theta is equal to 0. To get theta by itself, I take inverse sine of both sides. So we want to know basically what this is saying is when is sine 0? Well, sine is 0 when the y value on the unit circle is 0. And that happens in two places. It happens at 0, or another thing for 0, since we are on the interval of 2 pi, is 2 pi. And sine is also 0 at pi. So here are all the places where sine is 0. Because if you plug in sine 0, you get 0. You plug in sine 2 pi, you get 0. You plug in sine of pi, you get 0. All right, so now solving this guy, you're going to subtract the 1 and then divide by -1, and we find out that cosine theta is equal to a +1. How do I get cosine by itself? I do the inverse. So theta is equal to cosine inverse of 1. So we want to know, when is cosine 1? Well, that happens. Cosine is all about the x value. When is the x value 1? That happens only in one place, at 0 and 2 pi. So since we're just looking for the critical numbers, what's my answer? Well, I write out all the answers that I need. So my critical numbers are 0, pi, because I like to put them in order, and 2 pi. And there we go. I don't have to write the 0 twice, because once you write it once, it's covered. I don't write the 2 pi twice, because once you say it once, it's covered. There we go. There's number 9. All right, jumping down to number 10. Okay. So number 10. So I've given you this graph. All right. And in part A, you're going to think of this graph as the derivative graph. So this is not f, this is f prime. That's what f prime looks like. And it wants you to state the absolute / local max and mins for this. Okay. So a couple things to remember, that when you have a first derivative graph, okay, with a first derivative graph, we know that the zeros, okay, the zeros are possible max and mins. Again, that's because they're critical numbers. And then we also know that wherever f prime does not exist are also possible max and mins. The key being possible. You also know that when f prime is greater than 0, or in other words, positive, that means f is increasing. You also know that when f prime is negative, less than 0, we know that the graph of f is decreasing. So with this, I'm going to go look at my graph and I'm going to find my critical values, and then we're going to run my little number line to figure out some information. Okay. So we're going to say that this graph keeps going. I think that's one of the downfalls with this book, is that they, sometimes they want this as an endpoint, sometimes they don't. So we're just going to say that it keeps going. All right. So find me the zeros. We don't have to worry about f prime not existing, because there's nothing wrong up here. This is all continuous. Okay. There's no breaks, there's no hiccups, there's no open circles, there's no discontinuities or anything like that. This is all continuous, so that's good. So I've got a 0 here at -3. I've got a 0 here at 0. And I've got a 0 over here at +3. So there are my critical values. I've got -3, I've got 0, and I've got +3. So again, these are possible max or mins. We just don't know yet. That's why we got to look at the first derivative test. Okay. So again, we're breaking this up into intervals. We've got an interval from -infinity to -3. We've got an interval from -3 to 0. We've got an interval from 0 to 3. And we got an interval from 3 to infinity. Okay. Now, what we're looking at, again, remember, this is the F prime graph. Okay. So when we go from -infinity to -3 right here, this interval, we're looking at its location. We don't care if it's increasing or decreasing. That's not the question. What we want to know is when is it positive and when is it negative, because that will tell us what F is doing. So from -infinity to -3, my graph is under the x-axis. That means that F prime is negative because these are all negative y values. So from -infinity to -3, F prime is negative. So what does that mean F is doing? It's decreasing. So from -3 to 0, what are my F values? Well, they're all here above the x-axis. All these X values or all these Y values are above the x-axis, which means that they're positive. So from -3 to 0, all the Y values were positive. What does that mean F is doing? It's increasing. Ah, look, there's a change in direction. So what does that mean about -3? We now know that -3 is a minimum. In fact, it's a local minimum. Okay. Next one. What's going on from 0 to +3? Well, again, all my Y values are up here in the top half. They're above the x-axis. All these Y values are positive. Go back to my graph. So from 0 to 3, all of these were positive. So that means F is increasing still. So we now know that 0 is actually not a max or a min because there's no change in direction. Increasing, increasing, no change. So that probably means maybe 0 is an inflection point. I don't know. We would need more information. Okay. So from there, we got 3 to infinity. So 3 to infinity, my graph is below the x-axis. That means all the Y values are negative. So the Y values are negative. That means F is decreasing. Oh, we now know something about 3. Goes from increasing to decreasing. So we now know that 3 is a max. So there's our answers. And to be more specific, these are actually locals because we can't necessarily figure out if they're absolutes because we would need to know what the endpoints are for this. We would need to know, if these are, we'd have to be able to plug in, if these are endpoints or if it continues on. I mean, we really do need more information to determine if they're absolutes. but guaranteed for sure, locals. All right, so part B. So that was part A. Part B, you're going to focus in on this graph is now F double prime. This is F double prime. Well, let's talk about what we know about F double prime. Okay. With F double prime, the zeros are possible inflection points. And you know that if F double prime doesn't exist anywhere, those also create possible inflection points. Because you're looking at critical values here, critical numbers. Now in here, again, we're going to want to look at when F double prime is greater than 0, or in other words, positive. And we want to look when F double prime is less than 0, negative. Because when F double prime is positive, that means F on that interval is concave up. When F double prime is negative, that means the original function on that interval is concave down. So again, let's go find some critical values, and these are going to be possible inflection points. Okay, let's go find those critical numbers. Now, cool thing again, just like what happened in A, we do not worry about the does not exist because this thing exists everywhere. This thing exists everywhere. All right. So what are the zeros then? Well, again, they're going to be the same zeros that we had in part A. We've got -3, we got 0, we got +3. All right. -3, 0, +3. So these are my possible inflection points. I've already got my little number line. And again, we're going to look at what happens on these intervals from -infinity to -3, from -3 to 0, from 0 to 3, and from 3 on to infinity. Also, just so you know, part A has no bearing on part B. Okay, they're not connected. Okay. So looking at my graph, again, we're all about whether the y values are positive or negative. We're not looking at this graph thinking concave up or down. We're looking at the y values. So from -infinity to -3 here, my y values are negative. So that means y double prime is negative there. What does that mean for F? It's concave down. So looking at the next interval, from -3 to 0, all my y values are positive because we're above the x-axis. So the y values are positive. So that means we are concave up for the graph of F, whatever it might look like. From 0 to 3, again, same case. All my y values are positive. So that's another concave up. And then from 3 on to infinity, all these y values are negative. So that would be a concave down. So here's that information written in. So looking at this, whenever there's a change in concavity, that means you have an inflection point. So concave down to concave up, that means -3 is an inflection point. Concave up to concave up, that means 0 is nothing. Concave up to concave down, up, that's a change. So that means 3 is an inflection point. And there's our answer. That's all we needed. That's all they wanted. State the inflection points. Okay. There we go. That's number 10. Number 11. Number 11. So we're wanting to know what you know based off of the information. And again, it says that F double prime is continuous. So that's a good thing for us. That means that F prime and F should also be continuous and things like that. So nothing really too scary there. So we know in part A that F prime of -1 is equal to 0. And we know that F double prime of -1 is equal to -5. We want to know, what does this tell us about the original function? And then in part B, we know that F prime of 1 is equal to 0. We know that F double prime of 1 is also equal to 0. And again, we want to know, what does that tell us about the function? Okay. So let's take a look at our two problems. So whenever your first derivative is equal to 0, that means this guy's a 0. Remember? Zeros happen when F prime equals 0. So that means this guy is a 0. That means what we know is that since this is a 0, this is a critical value. Oh, sorry. This is a critical number, which means it could be a max or it could be a min. So that's what we know from this piece. Okay, it's a max or a min because that is a critical number for F prime. F double prime. So what we know here is that when we plug in that same value, the answer is a -5. So remember, when F double prime was less than 0, negative, what does that mean about F? F is concave down. So we know that F around -1 looks like this. So if I take these two pieces of information, meaning that this is a max or a min, and I know it has to look like this, we now know that, oh, this X value is actually a max because we are concave down on F around this number. So we now know that F has a local, because we're not sure if it's an absolute, we would need more information, max at X equals -1. So let's go see what we got here. At X equal -1, F has a, right there, it's A. There's our answer. It's A. Yay. All right, next one. So F prime of 1 is equal to 0. So we just talked about that. So we now know that this is a 0 because F prime equals to 0. So that means we know that 1 is a max or a min. We don't know which one. So let's take a look at this. Uh-oh, this is interesting. Again, this is another 0. But what does it mean when F double prime equals 0? So that means this is a possible inflection point. It's possible. So what does these two pieces of information tell us about F? It really only tells us one thing. And it goes back to this. Remember that zeros of the first derivative are where we have a tangent line that is horizontal on the original. With this information, we can't tell what's going on here. We need more information. The only thing that we really know is that F has a horizontal tangent line at x equals -1. Is it an inflection point? Is it a max or a min? We don't know. We need more information. So the answer to this one becomes D for part B. We need more. We don't have enough to know if it's a max or a min. Okay. Yes, Mr. Armstrong, this is fabulous. You're the best. I know. So let's keep going. So 12 and 13 are very similar to each other. They give us a list of information and then they want you to draw a graph. Okay, cool thing again, it's all multiple choice. But I'm going to write out this information and we're going to sketch a graph without actually looking at their pictures. So the first piece we know is that f prime of 0 is equal to f prime of 2, which is equal to f prime of 4, which is equal to 0. Okay. Then the next one, we know that f prime is greater than 0 if x is less than 0 and 2 is less than x, which is less than 4. We also know that f prime is less than 0 if x is between 0 and 2 or x is greater than 4. Okay. So we also know f double prime is greater than 0 if it is between 1 and 3, the x value. And f double prime is less than 0 if x is less than 1 or x is greater than 3. All right, so lots of information there. So let's talk about things that we know. So this really kind of divides into two pieces of information. Okay. So up here, this first statement is all about your critical numbers because these are all telling you the zeros when f prime equals 0. The second piece is right here. When f prime is greater than 0, that means it's positive. When f prime is less than 0, that means it's negative. So these two pieces are telling us when f is increasing because f prime is positive and when f is decreasing because f prime will be negative. So let's talk about this information. So we know that we have critical numbers at 0, 2, and 4. So we've got these intervals of -infinity to 0, 0 to 2, 2 to 4, and 4 to infinity. So let's talk about what f prime is doing, and then we'll know about f. So from -infinity to 0, where is that up here? Well, that's this guy right here, x less than 0. That's our -infinity to 0. So that is in the positive. which means that F is increasing. 0 to 2. Well, that's right here. So that means it is negative, which means that F prime or F is decreasing. Hey, now we know 0 is going to be a max because it goes from increasing to decreasing. And that was 0 to 2 right there. 2 to 4. Hey, there it is. So this is 2 to 4. And it is positive, which means we're increasing. Hey, change in direction. So we now know that 2 is going to be minimum. And then last but not least, 4 to infinity. Hey, there it is. This is our 4 to infinity, which is negative. So we know that F is decreasing out here. Hey, change in direction. So we now know that 4 is for sure a max. Okay. So let's take a look at the second half of the data. So this is all about F double prime greater than 0, but that just means that it's positive. This is all about F double prime being less than 0, so that all means it is negative, which is telling us about F. Remember, when F double prime is positive, that means F is concave up. When F double prime is negative, that means F is concave down. Okay. Now, the interesting thing is, notice that they gave us critical values up here. They didn't state any critical values down here, but they did. They're just trying to be sneaky about it. Your critical values are all based around these numbers that are right here. They are hoping that it is understood by just saying these two, that F double prime of 1 equals F double prime of 3 equals 0. They didn't write that, but they're making you think that this is understood by that statement there. Okay, by these little inequalities. So I'm going to draw my little number line. I've got 1, I've got 3. So we're dealing with negative infinity to 1, 1 to 3, and 3 to infinity. So we're talking about F double prime, and that's going to tell us what F is doing. So F double prime from -1 to infinity. Well, that's right there. So from negative infinity to -1. I said that backwards. No, not a -1. Mr. Armstrong, what are you doing? All these negatives. From negative infinity to +1, F double prime is negative. So that means we are concave down on F. From 1 to 3, hey, that's right there. This is our 1 to 3 interval. That is positive. So that means we are concave up. Hey, look at this. Changing concavity. That means we also know that 1 is an inflection point now for surezies. And then last but not least, 3 to infinity. That's right here. We see that that is negative. Okay, so that means we are concave down. Oh, change in concavity. That also means 3 is an inflection point. So all we do now is take this information that we know here, and we make our pretty little picture. All right. So I'm going to draw me a graph. Don't have to do anything crazy. So 1, 2, 3, and 4. because we really only deal with 0, 1, 2, 3, and 4. So again, we know that these are local maxes and mins. Okay. So they could be absolutes, but we really do need more information. Okay. So we know that at 0, we had a max. So I'm going to put that up here, put it high. We know that at 2, we had a min. So I need it low. We know that at 4, we had a max. Okay. So I'm going to put it high. Again, it could be higher than the 0. It could be lower than the 0 point. It doesn't really matter because they're not endpoints. Okay. We know that at 1, we have an inflection point. At 3, we have an inflection point. So I'm just going to put a dot that's kind of between these two, because that's a change in concavity. And I'm going to put a dot between 2 and 4, because that's a change in concavity. Okay. Now, we know that based off of this information, it's going to help us create the concavities that we talked about, that we're going to be increasing into 0. So we're going to be coming up to it. We're going to be decreasing into the 2. So coming down. We're going to be increasing into the 4 and then coming down after that. So we should be increasing into that, coming down into this guy, coming up into that, and then coming down. That's roughly what should happen. So as we draw our picture, just going to make it nice and wavy. Again, because I believe we are going on to infinity. So now you actually know some answers. I mean, granted, we weren't positive on, this could have been the absolute, where in my drawing, my 4 is my absolute, but we know that this is definitely just a local, and one of these two would just be a local. We just didn't have enough information to know which one would have been the absolute. But this is what the picture looks like, something like that, based off of my information. And you can see that from negative infinity to 1, we are concave down. And then from 1 to 3, we're concave up. And then from 3 to positive infinity, we're concave down. So that matches my data there. And I've got the increasing to decreasing to increasing to decreasing. And I've got all the max, the mins, and the reflection points, or not reflection points, inflection points. So the question is, which one of these graphs matches it? And if you look right here, it is D. D is the one that matches. And they actually had the 4 as the absolute max, kind of like mine. So the answer is D. Number 13, we're going to do the same thing. So this time, writing down the information, we got f prime of 5 is equal to 0. We know that f prime is less than 0 if x is less than 5. We know that f prime is greater than 0 if x is greater than 5. We know that f double prime of 2 equals 0 and f double prime of 7 equals 0. I just combined those together. So I said f double prime of 2 equals f double prime of 7 equals 0. We also have f double prime is less than 0 if x is less than 2 or x is greater than 7. We also have f double prime is greater than 0. Put a less than symbol. Wrong one, Mr. Armstrong. Greater than 0 if x is between 2 and 7. And we also have a new piece of information this time, that the limit as x goes to positive infinity of f is equal to 3. And the limit as x goes to negative infinity of f is equal to 3. So here's what we know. So again, all this information is the same as what we talked about over here as before. This is when we're going to be, sorry, that is not positive first here. This is our critical number, I should say, that this is a possible max or min. This is when f prime is negative, so that means this is when f is decreasing. Just gonna put that here. This is decreasing. This is when f prime is positive, so that means f is increasing. Again, these are going to be critical values that tell us if it is an inflection point or not. So this is all about max and mins. These are inflection points. And actually, let's go ahead and put that, let's change that up. We know they're critical numbers. This is a max slash min question mark. And then down here, these are critical numbers, but they are inflection point questions because these are possible inflection points. And then this is when f double prime is negative, which tells us that f is concave down. This is when f prime or f double prime is positive, which tells us when we are concave up. Now these two guys, because these limits are going to infinity, this is way back in our first module that we dealt with back in chapter 2. These are all about horizontal asymptotes. And this is the right horizontal asymptote. This represents the left horizontal asymptote. And they actually happen to be the same value. So that means we have one horizontal asymptote at y equals 3. So as my graph goes on to infinity and negative infinity, it should zero in on that line y equals 3. So that's important. That was the new piece here. But everything else is still the same. So I'm going to set up my little number line. We only have 5 here. And set up my other number line. We got 2 and 7. So we've got negative infinity to 5 and 5 to infinity. This is all about f prime. And we'll talk about what f is doing. Oh, can't see that part. This is all about f double prime and what f is doing. This is negative infinity to 2, 2 to 7, and 7 on to infinity. Okay. So negative infinity to 5. Where is that up here? Well, that's right here. That's this guy. This is negative infinity to 5. So it is negative. So that means we're decreasing. 5 to infinity, that's the second guy. So that means we're positive. So that means we're increasing. We now know that 5 is a min, a local to be specific right now. We don't know anything else. Okay. All right. So now we look over here from negative infinity to 2. That's this one right there. That's our negative infinity to 2. So we know that that is negative. So that means we are concave down. From 2 to 7, that's right here. This is our 2 to 7 interval. It's positive. That means we are concave up. So we now know that 2 is indeed an inflection point. And 7 to infinity is that last guy that's right there. And it's negative. So that means we're concave down, which now also verifies that 7 is an inflection point for surezies. All we're going to do now, take this information make a pretty graph. So 13, draw my quick graph. So we are going out to 7. So 1, 2, 3, 4, 5, 6, 7. 2, 4, 6. Okay. And I'll go out to 8. And then 1, 2, 3. I'm going at the 3 because we have a horizontal asymptote. So that's our y equals 3. All right, so let's plot some things. So it says that we have a minimum at 5. So I'll just put it down low. We have inflection points at 2 and 7. So because this is minimum, it's got to be up here because we do have a concave down. A concave down we have to create. So at 2 and 7. So I'll put one, I don't know, let's just put it right there where it's kind of a change. Okay, and I'm just going to make them even. And so we know that my graph has to hone in on each of these sides. And it's going to basically come decrease into that guy and increase out of that based off of the information that we just wrote up. Easy peasy, lemon squeezy. Let's draw it. So we know that our graph is going to come in here and then it's going to come swoop down. It's going to swoop back up and out. So there you can see the concave down. Here's the concave up. There's the back to the concave down. Okay. So there's what our graph looks like. We just got to go find our picture amongst the multiple choice. So it's not that one that's above. Hey, that one looks like it. So I'm going to say the graph is C. If you look at B, this is close to it, but you see how this starts to decrease and then this starts to increase, then decrease. And that's going against what we were talking about. Plus, these Y values are going away from the 3. We have a horizontal asymptote because these Y values over here should be going towards 3. And these Y values should be going towards 3 there. That's why this graph does not work, even though it's pretty close. But you have some, and well, the other thing is you're also creating maximums here. Okay, and we didn't have any maximums over here or above 7. So that's why it has to be C, because these are going to hone in on that 3. We're almost there. All right, number 14. This would be a problem that you would hand in to me if you were in my class. So we got this f of x equals 540x plus 3x squared minus 2x cubed. So what we are concerned about with here is the inflection point and concavity. So that means what we need is the second derivative. So let's get the first derivative. So the derivative of 540x is 540 plus derivative of 3x squared is 6x. And derivative of negative 2x to the third will be negative 6x squared. Okay. Derivative of f double prime, or sorry, the derivative of f prime, which will give us double prime. Well, the 540 goes away because the derivative of constant is 0. Derivative of 6x is 6. Derivative of negative 6x squared gives us negative 12x. So we want to talk about concavity and inflection points, which means that we're all about, again, critical values. So we want to find the zeros. in our case, when f double prime equals 0 this time. And we want to find when f double prime does not exist. So zeros, all we got to do is take 6 minus 12x and set it equal to 0. The does not exist case, we actually do not worry about, because this is a line. That line exists everywhere. There are no problem values. So we don't worry about that. We just got to find the 0. So if we find out what x is, you subtract 6, so you get negative 12x equal to negative 6. Divide by negative 12, so you get x equal to negative 6 over a negative 12. And you reduce that down, and you find out that our critical value is a half. So this is the possibility. So in order to answer the rest of the question, we make our little number line. So everything is about this half. And we want to find out what f double prime and f are doing this time. So I need, because we have equations, that helps us out. So I need a number less than a half to test. I'm going to choose 0. I need a number greater than a half to test. And all we're looking for is the answer positive or negative? So if I take 0 and plug it into 6x minus 12, or sorry, not 6x minus 12, 6 minus 12x. If I take and plug in 0, I find out that this answer will be positive, which means that f is concave up on this interval that's in here. So if I plug in 1, 6 minus 12 times 1, I find out that this is a negative answer, which means that I am concave down. Because there's a change in concavity, I now know that this is truly an inflection point. So let's get our answers here real quick. So we know that we do have an inflection point at 1/2, comma. Now, because it is a point, you do have to find that y value. So how am I going to find that y value? I need to take the 1/2 and plug it into the original equation. So I want f of 1/2, which will equal 540 times 1/2 plus 3 times 1/2 squared minus 2 times 1/2 cubed. Sorry, I know you couldn't see that. There it is. So that will give us 540 times 1/2. I'm going to go ahead and take care of all the powers. Plus 3 times 1/4 minus 2 times 1/8. Now, if I multiply, that will give me half of 540, which is, oh, I believe that's 270. 3 times 1/4 is 3/4. Minus 2 times 1/8 is 1/4. So in the end, you end up with 270.5. Or as a top-heavy fraction, (541/2). There's our inflection points. And we can talk about concave up and concave down. So we are concave up on this interval, which is from -infinity to 1/2. There's concave up, and we are concave down from 1/2 to +infinity. And that is what we are after. The inflection point, concave up, concave down. Okay. Moving on, we're almost there. We're almost there. I promise. Question number 15. 14, that question we just did, you would hand in to me if you were in my class. 15, you would hand in to me if you were in my class. So this is all about l'hôpital. So the limit as t goes to 0 of e to the 2t minus 1 all over sine of t. So the question is, can we use l'hôpital? So in order to use L'Hopital, you have to have what is called an indeterminate form. And that indeterminate form for L'Hopital must be 0 over 0 or infinity over infinity. And any type of infinity. It could be a positive infinity over a negative infinity, or negative infinity over a negative infinity. It doesn't really matter as long as it's infinity over infinity. So what we need to do first is make sure we have an indeterminate form, because if we do not have an indeterminate form, then you do not do L'Hopital. All right, so we plug in. That's going to give us e to the 2 times 0 minus 1 all over sine of 0. So just kind of a little bit of simplifying. That's e to the 0 minus 1 all over sine of 0. So my numerator, e to the 0 is 1. 1 minus 1 is 0. So as long as this denominator is 0, we can do L'Hopital because we're indeterminate. All right. So sine of 0 is definitely 0. Boom. We're going to L'Hopital this thing. So L'Hopital, when you do this, what you're going to do is you're going to put an equal sign. You're going to put an LH above it to let me know that you are L'Hopitaling. And you take the derivative of the numerator and the derivative of the denominator. So the derivative of the numerator, this is a chain rule. This is the outside. This is the inside. Derivative of a constant is 0. So what's the derivative of e to the 2t? Well, the derivative of e is just e again. And you're going to put the 2t back in the numerator. And we're going to multiply that by the derivative of the top, the inside, which is 2. So there's my numerator. What's the derivative of the denominator? Well, that will give us cosine t. Oh my gosh, made a huge mistake here. I forgot the limit. Silly Mr. Armstrong. There we go. That's much better. And now I can plug in. So we'll do direct substitution. So we'll have 2 e to the 2 times 0 all over cosine of 0. Well, that will give us 2 e to the 0 all over cosine of 0. As before, e to the 0 is 1. 1 times 2 is 2. So we know that we're not going to L'Hopital anymore because 2 is not a part of my indeterminate form. So we're going to get a limit here. Cosine of 0, well, that is 1. Oh, so that's nice. The limit of our original function as t goes to 0 is 2. Boom goes the dynamite. 16. Again, another problem that would get handed into me. So here it says the rate in milligrams of carbon per meter cubed per hour at which photosynthesis takes place for a species of plankton is modeled by the function. So we got this function P equal to 90I all over I squared plus I plus 1, where I is the light intensity, and that is measured in thousands of foot candles. For what light intensity is P a maximum? So we want to know when is P as a max. That's the big key to this. So in order to get P as a max, really what you're looking for is you're looking for those critical values, okay? We want to know the critical numbers of P prime. That's what we're after. So we need to take the derivative of this first. So in order to get P prime, this is going to be a quotient rule. So the quotient rule says that it is ho d high minus high d ho all over ho squared. So our high is 90i. Our ho is I squared plus I plus 1. So our d high is the derivative of this, which is just 90. Our d ho is the derivative of the I squared plus I plus 1, which gives us 2I plus 1. All we have to do is plug and chug. So we plug in. Our ho was I squared plus I plus 1, and that's being multiplied by d high, which is 90, minus our high, which is 90i, and that's being multiplied by d ho, which is 2I plus 1. And all of that is over ho squared, which is I squared plus I plus 1 squared. There we go. So we got some cleanup to do. So we're going to distribute through. We're going to FOIL through. So my numerator, I'm going to get 90I squared plus 90I plus 90 minus, well, 90I times 2I will give us negative 180I squared. 90I, a negative 90I times 1 will give us a negative 90I, because the negative will actually go through all of that as well. And I just did that when I FOILed through or distributed through, however you want to think about it. All over our ho squared. All right, so 90 i's are going to go away. We'll have a little bit of cleanup there. So that will give us negative 90i squared, because 90i squared minus 180i squared, negative 90, plus 90 all over I squared plus I plus 1 squared. And I would do one more thing to help things along. There's a GCF up in the top, and I would pull it out. And I would call that GCF negative 90i. And so that will leave me with I squared minus 1 all over I squared plus I plus 1 squared. I would take it that far, but there's nothing wrong if you left it like that. You're going to get the same answer in the end. But I always like to factor out GCFs because I think it makes things easier. So again, we're all after those critical values here. Okay, so those critical values are all about the zeros, which in our case, since this is rational, we only care about the numerator. So negative 90 I squared minus 1 equal to 0. And we care about when this does not exist. So that would be about the denominator equal to 0. So I squared plus I plus 1 squared equal to 0. So if we do some quick solving, divide by negative 90, really all you have left is I squared minus 1 equal to 0. If you solve this, you can factor this by difference of squares, or you can just add 1 over and then take the square root. You find out that I is equal to a plus or minus 1. Over here, for the does not exist, square root both sides. That will give us I squared plus I plus 1 equal to 0. So the question is, this won't factor. So you'd have to go look at a quadratic formula for this. So we really want to see, if we run the quadratic formula, does this give me complex answers? If it gives me complex answers, then we don't worry about does not exist. Okay, we just have these two pieces. So 16, dealing with the I squared plus I plus 1 equal to 0. Let me slide that down. So this is what we got to know about. So if we run the quadratic formula, I is equal to the opposite of B, which is a -1, plus or minus the square root of B, which is 1 squared, minus 4 times our A, which is 1, times our C, which is 1, all over 2 times A, which is 1. Okay? So from here, if you're kind of looking at this and doing some quick simplifying, it says -1 plus, that's a +1, minus 4. It's going to give us -3 all over 2. Because of that -3, we stop, and we actually do not have to worry about this case. It's junk, because that's complex. So in the end, our I is equal to this plus or minus 1. But because we're talking light intensity, we really don't have negative light intensity. So we're going to drop off the negative. So in the end, our answer, because it didn't want to know what the max was, but we'll talk about that in a moment, is 1,000 of foot candles. If we wanted to know the maximum, all you would have to do is take the 1 and plug it in here, which would basically be 90 divided by 3, which would be 30. So our answer, if we were looking for the maximum of this, would have been 30 milligrams of carbon per meters cubed per hour. But we weren't, we were just looking for the 1,000-foot candles. But that's how you would get the maximum. You just plug in what you just found. Okay. And also for this, I didn't do this, but you should verify that this is actually a maximum. So you could go to Desmos and plug in that equation and see that, oh yeah, at 1, that is a maximum. Okay, you should verify that. But generally, when you're working a word problem and you're looking for maxes and mins, you can count on that number being a true maximum. Okay. 17, another problem my students, if you have me, would turn in. And we're taking 2x times sine hyperbolic of 3x cubed. We got this 0.00, which tells me we are looking for the tangent line at that point. So that's what we're after. Cool. So that means in order to find the tangent line of this, we need the derivative. So the derivative of this is a product rule. So we need f times g prime plus f prime times g. So my f, I'll let equal the 2x. So that means f prime is equal to 2. My g will be the hyperbolic sine h of 3x cubed. Now the thing with this is a chain rule. This is the outside, this is the inside. So kind of give myself some space. So I need to take the derivative of hyperbolic sine, which is hyperbolic cosine. And you leave the inside alone. So there's the derivative of the outside. And now we multiply it by the derivative of the inside, which the 3 comes multiplies to 3. So that's 9. Subtract 1 from the power of 3, and we get x squared. So there is my derivative of the hyperbolic. So plug and chug now. Y prime equals f, which is 2x times g prime, which is 9x squared times hyperbolic cosine of 3x cubed plus f prime, which is 2 times g, which is hyperbolic sine of 3x cubed. And there we go. Some quick cleanup. Y prime is equal to, these two can multiply, so that gives me 18x cubed cosine hyperbolic of 3x to the third. Plus, and then this will stay 2 sine hyperbolic of 3x to the third. Okay. All we need to do now is plug in our x value, which was 0. We want to know what happens, what is the slope at 0. So that's 18 times 0 cubed times hyperbolic cosine of 3 times 0 cubed plus 2 times sine hyperbolic of 3 times 0 cubed. Well, because this 0 is out here multiplying everybody, this is all just 0 plus hyperbolic sine. Just going to go to my calculator and type that in real quick. I believe off the top of my head, I believe it's 1, but I want to double check that. Because sometimes my mental math is off. And it's good to check your mental math. Hyperbolic sine. So in here, this is all going to be 0. Because 0 times 3 is 0. So hyperbolic sine of 0. Oh, and it's 0. Look at that. I would have been wrong. So 2 times 0 is just 0. So my derivative, my slope is 0. Okay. Sometimes that happens. I think hyperbolic cosine was 1. Let me double check that one. See, this is why I always double check my mental math. See, I was wrong when I said hyperbolic sine of 0 was 1. I was off. So let me go to hyperbolic sine on my calculator. There it is, of 0. Yep, hyperbolic cosine is 1. Man. Always double check sometimes of that mental thinking. So we now know that the slope is equal to 0. And we've got our point of 0, 0. So all we got to do is y minus y1 equals m parenthesis x minus x1. So this is x1, this is y1. You do all your plugging in. Well, all of this is just going to go away. This is 0, so that'll leave me with y. So my equation is y equals 0. Because you'll have 0 times all of that. That's 0. This is 0. Y minus 0 is just y. There you go. And last but not least, number 18. This is all about limits and indeterminate forms. Okay, so they give us some information up here. They tell us that the limit as x goes to a for f of x is equal to 0. And the limit as x goes to a of g of x is equal to 0. And the limit as x goes to a of h of x is equal to 1. The limit as x goes to a of p of x is equal to infinity. And the limit as x goes to a of q of x is equal to infinity. So all they want you to do is evaluate the limit. And if the limit is indeterminate, then you say it's indeterminate. Okay? So we want the limit as x goes to a of f of x over p of x. We want the limit as x goes to a for part B of h of x, p of x. We want the limit as x goes to a of p of x plus q of x. And we want the limit as x goes to a of p of x raised to the power of f of x. All right, I have all that written down. Last question on the exam. So all we got to do is just use the information we know over here and start thinking about this. And if it gives us one of our indeterminate forms, please state indeterminate. If not, then give me the answer. So the limit of f of x is 0. The limit of p of x is infinity. This is not an indeterminate form. 0 divided by anything is 0. So there you go. There's only two forms for division. The only forms for divisions that are indeterminate is that an A or an I? It is an I. Thought so. So the two forms for division are 0 over 0 and infinity over infinity. And I shouldn't put an equal sign between that. That is incorrect, Mr. Armstrong. What are you thinking? So those are the only two indeterminate forms for division. Okay. Here, our h of x is 1 times our p of x is infinity. Well, this is not indeterminate. That answer is indeed infinity. Our only indeterminate forms for multiplication, let me look this up because I want to make sure I always tell you the correct information because indeterminate forms sometimes slip my mind. For multiplication are when we have zero times infinity. Okay. All right. Continuing on. Here, the limit as p of x goes to a is infinity, plus the limit as q of x goes to a is infinity. While infinity plus infinity is infinity. That is not an indeterminate form. The only indeterminate form we have for subtraction is infinity minus infinity. This is not indeterminate. Infinity plus infinity is infinity. Okay. And last but not least, P of X is infinity. F of X is 0. This is indeterminate. We don't know the limit of that. That does become indeterminate because we have 3 power ones. Here are the indeterminate power ones. The indeterminate power ones, as you can see, are infinity to the 0, 0 to the 0, and 1 to the infinity. And that's what that last question looks like. 3 of them we were able to figure out. The last one was indeterminate. That's how it works. And with that being said, that wraps up exam 3 review. Thank you for stopping by.